was still muted.
It is a pleasure to introduce our next speaker, Hu Byung. The title of his talk is Smoothness of Markov Partitions for Expanding Toral Endomorphisms, Part 2.
Thank you, and thank you for giving me the opportunity to speak here. This is the first time I'm doing a talk like this, so it's exciting for me. I hope it's also exciting for the audience. As the title says, this is going to be part two of the talk that Chase just gave. So we're going to see a little bit more of the same and some extra stuff. Oh, nice my. There we go. So I'm going to briefly recap the setup just for the sake of completeness. I won't spend too much time on it. And then I'm going to dig into the case of non-diagonalizable two by two matrices. So the smoothness of Markov partitions in this case. And then I'm going to talk a little bit about the Hausdorff dimension. We have a fractal object and we want to know, or a non-smooth object, and we want to know something about the Hausdorff dimension. And I think it also bears repeating that Chase and I are new to this subject, so we very much welcome any kind of feedback, comments, or pointers to related results that we should be aware of. So let me recap what we're doing. We have a D by D integer matrix A, and any eigenvalue of A has modulus strictly bigger than 1. This induces a map on the torus by acting on coset representatives by matrix multiplication of column vectors. And we'll call this induced toral endomorphism, we'll call it FA or just F. We have a Markov partition, which is a cover of the torus by closed sets with disjoint interiors. And they have this Markov property, which says that if I hit a rectangle with another rectangle after applying my map, then I should hit the entirety of it, and I should do so in a somehow injective way. The picture that you should have in your head for these things is that the image of a rectangle is a bunch of other rectangles. And the reason we call them rectangles is for historical reasons. One of the first places where they were developed, they actually looked like rectangles geometrically. Um, and the thing we're interested in is the boundary. So this is partial M, which is the union of the boundaries of the rectangles in the partition. We saw all of this. We saw that Markov partitions exist. We saw that their boundaries are nowhere dense and that the boundary is invariant in the sense that the boundary gets mapped to the boundary. And for this talk specifically, I want to focus on this case of hybrid. So here it's kind of an arbitrary choice of what we call hybrid, but we mean that the boundary of a Markov partition is not smooth in the sense that it's not piecewise smooth, but it does contain a smooth arc. And so the reason we introduce this term is to give some sort of a qualitative, a name to qualitatively different behavior from the nowhere smooth, or essentially nowhere smooth case, and the smooth and linear cases. So we'll see an example of what that looks like. And then the reason we care about Markov partitions is that they give a symbolic coding of a system. Um, all you need to know here is that it gives a covering map from a space of sequences where the entries in the sequence correspond to a rectangle, and this map is good in many different ways. Basically, in most ways that you would want to study a Toral endomorphism, we can obtain a lot of that from just this symbolic coding when it exists. Right, this map preserves entropy. It's one-to-one on a density delta set. Um, for the argument in the Hausdorff dimension that we'll see, we're gonna use this symbolic coding. So I will touch a little bit more on that later. Let me also restate the main theorem, which says that if I have a 2 by 2 expanding integer matrix A, then the corresponding Toral endomorphism admits a smooth Markov partition if and only if some power of the matrix is diagonalizable with integer eigenvalues. And then we saw already in Chase's talk, we saw these sort of two distinct cases of what happens when I have two irrational eigenvalues with different modulus, or if I have complex eigenvalues with an irrational argument. Um, and it turns out that there's a little bit of sort of a two-step argument or a two-line argument, I should say, that tells you that this is the only thing you have to worry about when your matrix is diagonalizable, in the sense that all the other cases give you that some power of the eigenvalues is going to be an integer. This uses like the rational root theorem. Um, the case for non-diagonalizability is the same but slightly different. And the argument also requires a little bit more. In spirit, it's going to be the same, but there's one extra detail that we need to take care of. And in order to do this, we need to use this sort of well-known lemma, I guess, that if I have a an integer k that's not -1, 0, or 1, then the k multiplication map on the torus, the one torus or the circle, uh, has a point with a dense orbit, and therefore has a dense set of points with a dense orbit. This is easy to see. You take the base k expansion of your points in the torus. That's and then a clever choice of point will give you this. Um, much as before, if we have a matrix that's not diagonalizable, but it's only similar to a Jordan block, then the change of coordinates does not fundamentally change our argument. So for convenience, I'm going to assume that I actually am dealing with a Jordan block itself. So a matrix K1, 0K. And I have a Markov partition M. And in this case, something that we need to note is that if I have this Markov partition, then its boundary must have some kind of vertical component, in the sense that if I look at this picture here, where I have sort of in the green dotted line outlines the torus. So you should think of opposite sides of the green lines as being identified. Um, and the black lines here are the boundary of a supposed Markov partition. So this is sort of a collection of cylinders that wrap around the torus. This is not a Markov partition, because if you look at one of these strips, it gets doubled in length in the x direction, or at least doubled, right? It gets multiplied by k, but k's uh, absolute value at least 2. So it's going to get doubled and intersect with itself on its interior, which breaks the injectivity that we want. So we're going to have a curve with some kind of vertical change. And we're going to suppose that this is C1. So we have a curve that's C1 contained in the boundary, and its tangent vector has a vertical component. I'm going to blur the lines between whether I'm on the torus or whether I'm in R2, so the universal cover. Hopefully that doesn't cause any confusion. So I have a tangent vector with a vertical component, and by the lemma, I'm going to make it so that gamma 0, so the base point of the curve, has a dense orbit under the k times multiplication map. So the y coordinate is dense in the vertical direction. So really here, this should be, the projection from R2 onto the torus, and then the projection onto the y-axis. But for the sake of notation, I hope it's clear like this. And this is sort of the difference between the previous case, because in the previous cases, we saw that the base point of the curve can be arbitrary. Here, we need to actually make a specific choice for it in order to get the contradiction. But we know that we have a curve with vertical change, and so we can always find this such a base point. If I take A and I raise it to some power, I'm going to get this matrix here on the right, where the top right corner has this extra factor of m, which means that it's going to be much bigger than just k to the power m. And if I take these powers of A and I let them act on column vectors then the ratio of the two coordinates is going to go to zero, which means that much like before, we're going to get whatever vector we start with, it's going to get stretched out along a horizontal line. So the picture here, you should think of the leftmost black line as being gamma prime at zero, and then increasing iterates of that vector. They're not to scale. I rescaled them to make the picture a little more clear, but the main thing to notice is that the angle goes to zero and the lines get longer and longer. Um, Also, because we chose our y coordinate to have a dense orbit on the circle, that means that if we iterate our matrix on this base point, we get a dense y coordinate. So essentially, this stretching out gives us the ability to approximate any x coordinate that we want for any point in the torus. And our choice of base point gives us the ability to approximate any y coordinate. Um, so if I take my iterate of the matrix to be big enough, then I can get very close to any point. So all that to say, let me just repeat, I guess. I have a curve I presume to be C1. I iterate my matrix A on it so that my y coordinate is as close to some arbitrary point in the torus as possible. And then I can keep iterating that to make the tangent vector sufficiently horizontal, which means that the curve itself also has to be sufficiently horizontal. But we assume that the curve is contained in the boundary, which we know is nowhere dense. So this is the same contradiction that we reached in the previous argument. This point about vertical change is kind of crucial to this argument, right? So what we've shown is that any curve in the boundary that has a vertical change cannot be C1. And actually, that's as much as we can say because uh, in this case, there's a construction due to Bedford, which explicitly uses fractal techniques, um, which allows us to make a Markov partition for any expanding endomorphism. And when you use this technique for, say, the matrix 2102, so a Jordan block, you get the picture here. So here again, the dotted green lines are the outline of or sorry, are sort of the identified sides of the unit square. And so I have a Markov partition consisting of four tiles, right? The two tiles that are entirely outlined in black, and then the two parts on the left of this square are sort of halves of the tiles on the right. Um, and you can see here just by sort of observation, well, this has a lot of linear components, and linear components are actually smooth. So this gives me something hybrid. And actually here I have a linear part at every, excuse me, um, at every dyadic rational. If I took this matrix to be, Jordan block with the eigenvalue k for some other integer, then I would have the same picture, but I would have uh, I would have k squared tiles, and here the pattern is sort of goes in twos, but in the arbitrary case it would be sort of a k times repeating pattern. But spiritually it would be the same. So this is hybrid behavior, and this can sort of this can happen with Jordan blocks and non-diagonalizable matrices. And if I go to higher dimensions, I can start taking, product systems. And this is also another way of obtaining this hybrid behavior. Again, by our specific choice of what we call hybrid. So if I take a 3 by 3 matrix that looks like this, then I can think of the top left component as a 2 by 2 matrix, which turns out to be expanding, or which will be expanding. And this particular matrix has eigenvalues that are not roots of integers. So whatever Markov partition M I make for this 2 by 2 block on the two torus cannot be smooth. This is what we saw this earlier. But because I have a sort of standard doubling map in the third coordinate here, I can take this non-smooth Markov partition and take its product, the Cartesian product with two halves of the interval. And this is a Markov partition for A, which is sort of not smooth, but it has linear parts in the Z coordinate. So the rectangles here are sort of, you take like a fractal two-dimensional thing and you stretch it out along an interval in a linear way. And this is another way of obtaining hybrid behavior. Um, we have something non-smooth, so can we say something about the Hausdorff dimension? And we can say something. Uh, let me state the theorem and then I'll say something about it. So I have my expanding Toral endomorphism. I have M a Markov partition for this endomorphism, and then I take lambda to be the modulus of the smallest eigenvalue. Then the Hausdorff dimension of the boundary of this Markov partition is going to be at most the ratio of the topological entropy of my system restricted to the boundary, right? Remember, our boundary is invariant, so I can this is a dynamical system on its own, divided by log lambda. And this shouldn't be a surprising bound in the sense that often we can express Hausdorff dimension as the ratio of a of entropy and a Lyapunov exponent. And here, this lambda is like a lower bound on the Lyapunov exponent, or I guess I should say that log lambda is a lower bound on this exponent. Um, but this is the argument here can be extended to other cases as well, and I'll touch on that in a second as well. The idea is to use the symbolic dynamics that we get from the partition. So the first thing I need to do is I make my partition sufficiently small, which I can do in a way that's fairly natural. I need to take sort of inverses of rectangles and then intersect those. But this won't change the Hausdorff dimension because my map is locally bilinear and therefore locally bi-Lipschitz. So this geometrically doesn't change anything. And then for the small partition, I'm going to take the symbolic cover. So a shift of finite type, a sequence of a space of sequences on symbols that represent rectangles. And because the symbols correspond to rectangles, if I look at a pair of symbols, this corresponds to a pair of rectangles, and I can ask whether or not those two rectangles intersect each other. This will give me these symbols and the sort of corresponding transition relation will give me a new SFT, a new shift of finite type that I'm going to call E here. And this in turn gives a cover pi prime or a covering map pi prime from E onto the boundary. And this exclamation mark here is not a factorial. This is to convey excitement about this project. I should also point out that this technique is sort of if you're familiar with the Anthony Manning's work to show that axiom A diffeomorphisms have rational zeta functions. This construction is similar to that. It's an adjacent construction. Okay, so I have an SFT and it covers the boundary in a way that commutes with the dynamics. So if I take a cylinder set in this SFT, well, it's a shift on pairs of symbols. So that means that a cylinder set is corresponds to a pair of words where the respective words are words from the original symbolic cover X. So here I sort of use this bracket notation to mean a cylinder set specified by the words W and W prime. And because of how I defined my map pi prime, the image of the cylinder set of these two words is actually the intersection of the pi image of the cylinder sets of the individual words as thought of as cylinder sets of X. And then the intersection of that is, of course, contained in the union of the two sets. Um, and so if I specify, if I fix some n, then I can take all words, sorry, all pairs of words of length n, which covers all of E. Um, and then the image of that covers all of the boundary. Um, there's an argument from Ashley Kitchen Stafford, which is also the paper that gives the definition of Markov partition that we use, that says that with our choice of lambda, the diameter of the image of the cylinder sets as cylinder sets of X uh, shrinks like lambda to the power minus n whenever we have long enough words. And because we're going to compute a Hausdorff dimension, we'll end up with long words anyway. So if we fix some positive real number, non-negative real number, then I can compute the Hausdorff dimension in the way that we normally do. Um, here I take my pairs of symbols. I'm sorry, my pairs of words that give me cylinder sets in E. I take their image and then which cover the boundary. The diameter of those is going to be bounded by the diameter of the union of the images of individual cylinder sets, which we know to decay at a rate lambda to the minus n. And then what we need to do is, because we only have to worry about words from E, because our boundary is invariant, I can count how many of those pairs of words I have. And because E is an SFT, this is actually sort of order mu to the n, where the logarithm of mu is the entropy of E, the topological entropy. And if you look at this expression, well, if S is strictly bigger than the ratio of the logarithms of mu and lambda, then this goes to 0. And it turns out that my pi prime is also uniformly bounded to 1. So there's a uniform bound on the number of pre-images that a point has under this map, um, which means that it preserves entropy. So I have not only that log mu is the entropy of E, but it's also the entropy of F restricted to the boundary. And then that identification gives me exactly the bound that I was looking for. So the Hausdorff dimension of the boundary is at most the entropy of our dynamics restricted to the boundary divided by log lambda. This is sort of this is a bound. It's weaker in higher dimensions and when there's a big gap between the eigenvalues. But we can attain equality. So if I have the 2, 0, 0, 2 matrix, then I take this Markov partition of 5 by 5 of a 5 by 5 grid. I choose 5 here because I want remember that I need my rectangles to be sufficiently small, and it turns out that side length 1/5 is small enough. And you can see that the entropy of F restricted to this is log 2 because it's a finite union of circles. And in that direction, we only have doubling. You can also compute E like explicitly here, which takes a little bit of work, but it will give you the same answer. One thing to note about this argument is that also it works for non-Toral maps that admit a Markov partition. The notion of lambda becomes a little more it is not exactly an eigenvalue, but it's a lower bound on the expansion. And so I can do it for general systems that expanding systems. Oh, this is a typo. This should be expanding. But I can also do this in the case of invertible systems. And for invertible systems, the definition of a Markov partition is it's a little more involved. but a similar argument works in that case. Even though the boundary itself is not an invariant set in the way that we have for expanding systems. So this would, for example, apply in the case of hyperbolic Toral automorphisms. Um, and then we have a bound it's almost the same expression. There's an extra term, but the same technique works there. Um, and I think that's it. I think I'll stop there. So thank you.
Yes, thank you. Any question to the speaker? So if there is no question, let us thank the speaker again. Our next talk will start in 4 minutes.
Thank you.